All right, so this week we're going to be taking a look at one section, okay, which is vectors. We're just going to split it up into 4 different days. Now you'll notice that when you do the homework, it's from a different book. So it's going to say 8.5 part 1 from class. That's what's in like the book we've been using all year. When you look at the homework tonight, it's going to say 5.4, but it is the correct PDF. It's just a different book. I think it's 5.4, and then when we get to the next part, it's 5.5, and then 5.6. Those are the sections from a different book. All right, so what is a vector? Well, a vector is basically used to represent a magnitude and a direction. What's an example of something that has those two things? Velocity. If you want to describe basically the way that an object is moving, you would tell me its velocity. Now sometimes people, when they think velocity, it just means how fast it's going. Nope, it doesn't just mean how fast it's going. It means how fast it's going and what direction is it going in. Okay, that's velocity. Another example of a vector is force. You might think, well, how does force have 2 parts to it? Well, the magnitude of a force is how hard, let's say you're pushing on an object. That's how hard you're pushing. That's the magnitude. The direction is which way are you pushing? Are you pushing it away from you? Are you pulling it towards you? Like what are you doing? Which way is your force being exerted? Right. So if you want to look at this is an example of like all different flights, okay, in the area. And each one of these planes is a vector. Right. If we click on one, we can see its magnitude and its direction. So in the case of velocity, magnitude is how fast it's going. So that's the magnitude, 437 miles per hour. The direction, well, on an airplane they call that a route. So if I click decode, it'll tell me this plane has changed directions a few times, but it'll tell me the different directions that it's been traveling. These angles that you see, those are compass headings. Okay. Compass headings. Right? But every plane on that grid has a magnitude and a direction. And it's the job of the air traffic controller for that airport to make sure all those planes, in theory, stay safely spaced apart and keep everybody safe. It might look like 2 planes are really close, but these 2 planes, I mean, they could be 50 miles apart. They could be really far apart if we zoom in. And even 2 planes that are right on top of each other, one of them could be at 30,000 feet, one of them could be at like 5,000 feet. So they could be still very far apart. Right, but think of those as all different vectors. What's that?
No, I thought the blue was the sea, the ocean for a sec, so I thought it was like England. But it's
the blue, yeah, that's probably a little bit of snow and rain kind of mixing. Yeah. And the purple's probably ice, I would guess. Yeah. So you notice, I don't know if it's on purpose or not, but there's no planes around that purple spot right there because it's ice, so they might be going around it, so they don't have to go through it. Or maybe they could go above it and there's just nobody at that point right now. I don't know. Right, but apparently right here they're flying right through, or they're flying above it. It's hard to say. We don't know. Because if you're above the weather, then there's no problem. All right, so one thing we can't tell by looking at all those planes is we cannot tell how fast they're going. Right? We can see the direction just by looking at the way the plane is pointing. But without clicking on it, I can't tell you how fast that plane is going. So one way that we can draw a picture that shows us how fast it's going is to use an arrow. What do you think I could do to my arrow to represent it, to make it represent a plane going faster? Any guess how I could draw my arrow differently if the plane was going faster?
Bigger?
Do what?
The arrow, you can do it longer.
Yeah, you do it longer, exactly. So like if you've got a plane like this and a plane like that, that would represent two planes traveling in the same direction. But the bottom one is traveling faster. So when you draw an arrow, the length of it represents the magnitude. And then the way that the arrowhead is pointing, well, that's the direction. Now, drawing vectors out, it's not always the fastest way to do things with vectors. I would say it's really good to draw it out when you have a word problem, so you can kind of see what's happening. But if we don't have a word problem, eventually we're going to get away from drawing it. And I'm going to show you faster ways to do it. But when you're starting out, if you've never done vectors before, drawing it does kind of help you visualize what's going on. Okay. So any question what a longer arrow means it's a greater magnitude. And to know what magnitude means, you have to know what kind of vector we're talking about. If we're talking about velocity, magnitude is how fast it's going. If we're talking about force, it's how strong the force is, like pushing on something. Okay. When you draw a vector, it has a starting point and a stopping point. We call the starting point the initial point, and the stopping point is the terminal point. So in geometry, some people say, well, it looks kind of like a ray, because a ray is like an arrow. The difference is, when you draw a vector, it stops. It does not go on forever. And a lot of times when we name a vector, we use a single letter. But what do we already use single letters for in algebra?
Sides.
I'm thinking a little bit more, think more general. What is a letter used for in algebra? A letter is used to represent a well, what do you call a letter in algebra?
Variable.
A variable. Yeah, we call it a variable. So the problem is, if you want to use a single letter to name that, we already use single letters for variables. Well, it can't, the name that you give this can't look the same as a variable. It has to look different, because this is not a variable, this is a vector. So what we do, to make the name look different, you can do one of two things. When you name a vector as a single letter, you can either put an arrow on top of the letter. That arrow indicates that it's a vector, or you can make the letter bold. That's how you make it look different than just a regular variable. Most of the time, the way I'm going to do it is I'm going to make my letter bold. But you might see me use the other notation as well. Now you can name a letter, you can name a vector using any letter you want, except there are 3 letters you are not allowed to use: I, J, and K. And you cannot use I, J, and K, and there's a reason for that, which we'll talk about tomorrow or Wednesday. Other letters I wouldn't use just because they look like numbers. I wouldn't use a O, because that could look like a 0. You know, an S could look like a 5. But I, J, and K, that's a separate thing. So M, W, X, Q, V, W, any of those are fine. All right, so now, let's say that we had a boat, like that. And that boat is floating, maybe it's on like a little pool or something. And we take a fan, and we aim one fan at the boat, going like this. and then I aim another fan, same power, same strength, aiming that way. What's going to happen to the boat?
It's going to go off at a 45-degree angle.
Yeah, the boat's going to move at an angle up and to the right. What's going to happen is these two forces, the fan blowing up and the fan blowing to the right, are going to combine together. When they combine together, you're going to get that as a result. What I just did right there, that is how you visually add two vectors together. I'm going to show you and write down exactly what I did. But that's what's going to end up happening. The boat is going to go in the direction that goes up and to the right, and that's going to be the magnitude of the wind that blows it. So, when you combine this vector with this vector, you get a new vector. Okay, that's the important thing. Combining two vectors together with addition gives you a new one. Okay, that new vector can point in a different direction, and it can have a different length. It depends what happens when you combine them. And in general, the quick way to add two vectors visually, I'll do it one more time before I write it all out. If you have one like that, and then you've got one like that, you line the two vectors up, what's called head to tail, right? Connect the beginning of one vector to the end of the other one. So you line them up just like that. Once you line them up, so the beginning of one and the end of the other are together, you draw in the third side from where you started to where you finished. So that vector in green represents combining the red and black one together. That's it. So I'll kind of write that out now. So if you want to add two vectors together, you line them up so that if this is V, just draw V, and this is W. You line them up so that the end point of V, right there, is right in line with the starting point of W. Just like that. So that's the first step. Last step, you're going to draw in the third side of your triangle. And the way you draw the third side in is from the start to the finish. Just like that. Well, yellow is not a great color. I don't know how well you can see it. But this vector in yellow is V plus W. So that's it. Okay, one downside of adding them visually, if they're big, they can go off the paper. So we got to make sure that we have a piece of graph paper big enough to do it. All right. So any questions on how you line two vectors up to add them visually? All right, let's try adding these two. So can someone explain to me, how do I line those two vectors up so I can add them?
Put the initial point of V and coincide it with the terminal point of W, or is it the other way around?
The other way around.
Gotcha.
So you want to do where V ends. I would put that like right there. And then where W starts. Just like that. All right, so that's how you line them up. And what do I do from there?
Connect the initial point of V to terminal point of W.
Yep, perfect. Connect the initial point to the terminal point. I know you can't see the arrowhead because it's It's a little bit smaller, but that's the answer for V plus W, right there. So for the first, so I gotta get off yellow. For the first two problems, or first couple we're doing, the answer is an image. We're gonna draw a sketch. All right. Any questions on that one? Did you all right?
Yeah, just more than enough sleep time. All right.
All right, so that's adding V plus W. All right, let's try this one. Anyone have an idea what's going to happen when you add those together?
2 equals 0.
Yeah, they're going to kind of cancel each other out. You're supposed to line up where V ends and where W starts. So you need to line the blue dots up. Once you line them up, you're going to connect the beginning of V to the end of W. So line the blue dots up and then connect the green dots. But watch what happens. If I line the blue dots up, well, the green dots also line up. So I can't really draw the answer to this one. But what did we say earlier? When you add two vectors together, you always get a what? You always get a new vector. When you add two vectors together, you always get a new one. So, you cannot write the number 0 for this. The answer to this problem is not the number 0. It is the vector 0. That's the answer. So you can either draw it with a 0 with a arrow on top, or what's the other way I could do it? Yep, make it bold. So you can write your answer either way. But if you put 0, the number, that's wrong. Okay. One thing we can do with vectors, just like you can do with regular numbers, is the order you add them in doesn't matter. That's the commutative property. So let me show you that first. Okay. What I'm going to do is I'm going to take V and W and add them in that order. Okay. Here's V. I'm going to put W right on the end, and I'm going to draw my answer. That is V plus W. I'm just going to put that off to the side. Now I'm going to reverse it. Instead of V plus W, I'm going to take W and I'm going to put V on the end of it. That is different than what I did before. But let's see about the final answer. Connect where you started to the finish. That's W plus V. Now compare the two by lining them up. What do you notice?
The same?
Yeah, they're the same thing. And it actually doesn't matter how many vectors you have. If you had one like that, and one like that, and you wanted to combine all three of them, you can connect them in any order you want. You could do this. The only thing is they have to follow a path. All the arrows have to be, the end of one arrow has to be connected to the start of the next. You can't do that. No. Think of it as like a one-way kind of flow. All right. And if you draw in the answer there, see what you get. Now, what's the order I connected them in? I did red, green, purple. Right. Let me do it in a different order. Let's do green, red, purple. Green, red, purple. That's a different order. But look at the answer. It's not perfect because I didn't use a grid, but it's the same thing. So adding vectors together, order does not matter. The other thing that doesn't matter is grouping. Okay, I'm not going to demonstrate that one, but you could. Grouping is just changing what you add together first. So think of like an example with numbers. If you do it the way that's on the left, what's 1 plus 2? 3. And then plus 3 gives me 6. Now the way that's on the right, what's 2 plus 3?
5.
5 plus 1?
6.
It's the same thing. Right. And that works with vectors as well. Changing the grouping when you add vectors together gives you the same answer. Any questions on that one? Okay, those are two pretty straightforward properties for vectors. How about that? What do you think the difference, if I were to draw these out, would be between the vector v and the vector negative v?
The direction,
Yeah, can you be more specific about how the directions would compare?
the negative v would go in the opposite direction of the v.
Right, they would go in exactly opposite directions, or you could also say 180-degree rotation. Yeah, exactly opposite directions. What would be the same?
The magnitude.
Exactly. They would have exactly the same magnitudes. So that formula on the bottom, that's an example of what we did earlier. We added two vectors that pointed in exactly the opposite directions, and we got this. What did I call that again? What do we call this thing?
Vector 0?
Yeah, the zero vector.
The
Yep.
zero vector.
Yep. That's it. Yep. All right, so now let's say that I had some arithmetic. Right? I was trying to teach somebody how to do subtraction, and they don't understand what this means. But they do understand everything about addition. How could you change this from a subtraction problem to an addition problem?
Put the -1 in parentheses and then addition sign.
And let's just keep the order the same.
So 4 minus -1 works. If you want an addition,
Well, I want addition, but I want it to also be equivalent to that. What can I do with addition that gives me the same answer as this subtraction problem? Like pretend you had to type that in on a calculator and your subtraction button is broken. How are you going to type it in without the subtraction button?
2 plus 1.
No, you got to use the same numbers.
Oh.
You got to stick with pressing the 4 and the 1 button. So you got to stick with that.
You can't use the subtraction.
You can't use the subtraction button. That's the only button you can't use. You can't use this button right there.
But you can still use that one at the bottom next to the dot.
Sure.
Can you not do 4 plus -1?
Yeah. We can do 4 plus -1. That's exactly the same as 4 minus 1.
That's what I was trying to say earlier, but you told me to keep it in the same order.
Yeah, I just meant keep the 4 first and keep the 1 second. Yeah, so 4 plus and then -1. Yep, that's perfect. So when we want to subtract two vectors, that's how we're going to do it. We're not going to think of it as subtraction. We're going to think of it as addition of the opposite. Adding the opposite is subtraction. So to subtract two vectors, what you're going to do is take the second vector, flip it, right? That's going to give you the opposite, and then add it onto the first. All right, let's try this one. It says to find v minus w. Well, first, can somebody tell me how I'm going to think of this problem as addition instead of subtraction?
V plus -w.
Yep, perfect. We're going to add -w onto the end of v. Okay. Well, I have w. How do I get -w?
Reflect it over the, or just mirror it, basically.
Yeah, you can reflect it. You have to reflect it twice, though. So you have to flip it left, right, and then flip it up, down. And that will completely rotate it 180. Yep. So there's -w. Now, take v and put -w on the end of it. You just did subtraction. That is v minus w. And draw in your answer. So it's going to look about like that. That's v minus w. Okay, so any question on how to do subtraction? Just flip the second one around and add it on. Now again, is that the fastest way to do subtraction, having to draw it like that? No. But it's an easy way to start when you're just learning about it. Okay, what do you think something like this would do? If I put the number 3 in front of v, anyone think they know what that would do to v?
Multiply it.
How about if we were to draw it? How would it look different than v?
It'd be longer.
Yes. So when we scale a vector, it's actually one of two things can happen. Well, actually, technically one of three things. In this case, putting the number in front made it longer. That number that you put in front of a vector, like in this case it was a 3, that is called a scalar. When you scale a vector, you get a new vector. So we just saw one thing that can happen. When you scale a vector, the vector can get longer. There's a second thing that could happen.
It could get shorter.
It could get shorter. And the third thing that can happen, it could reverse direction. What kind of number would you have to scale by to make it reverse direction?
Negative.
A negative, yep. So that's the three things that can happen when you scale a vector. Okay. This is called a scalar product. You can also call it scalar multiplication. It gets longer, it gets shorter, or it can reverse direction. Now, when we are scaling vectors, this is where drawing can really become a pain. If you had to scale something to be like 30 times as big, you could very easily go off your graph paper. So when we scale things, we're going to try to keep it manageable. All right. So they're giving us v, and they want us to find 2v and 1/2v. Okay, I don't want to use a ruler. Remember, this V is bold. How could I get 2V exactly on the smartboard without using a ruler?
Make a duplicate of V and attach it.
Yeah, just make a copy of it. I'll make 2 copies. That's V. Put that on the end of it, and then actually draw your final answer. So 2V would be just like that. Okay, how about 1/2 V? There's no way I can do it exact. But how is 1/2 V going to compare to V?
It's gonna be half of it.
Yeah, it's going to be half of it. So I'm just going to kind of estimate that. Maybe, I don't know, about like that. Any question on that? All right, let's try a scalar that is a negative. What's going to happen when I do negative V? How's that going to compare to V?
The direction's gonna change.
Yep, how about the length?
The same.
Same.
Same, exact same. I know I could copy it and flip it twice. I'm just going to kind of estimate this time. So that's negative V. And how about negative 1/3 V?
The direction, the size is gonna change.
Yeah, this is going to change both. It's going to make it 1/3 as long, and it's going to flip it. Well, I just flipped it last time. So then just try to estimate about negative 1/3. Okay. Any question on that? So scaling is pretty straightforward. Now, let's combine, I'm just going to do the first one. Let's combine scaling and adding at the same time. 2V plus 3W. So when we're done, we're going to stack 5 vectors together. V is up and to the right. W is down and to the right. That means I want to start on the left. Okay, in order to have plenty of room to do this problem. Put your arrows on the left side. Okay. How many copies of V do I need?
2.
I need 2 of them. So let's make 2 copies. And we'll put 1 there and 1 right there. Okay, so there's 2V. And how many copies of W do I put on the end of that?
3.
3. So let's make 3 copies. All right, there's 1, 2, and 3. So that's 2V plus 3W. And what's my last step?
Make the new vector.
Yep, and how do I draw it from where to where?
From the start point of the first one
Yep, the start point of my first vector V
to the end point of the last one.
to the end point of the last one, which was W. And that is going to be the result if you combine them all together. Just like that. 2V plus 3W. All right. Any question on that? All right, so that's pretty much what we're going to do for visual stuff. So the last thing I'm going to show you is how we can write some vectors without drawing. All right, and to do that, I need to start showing you some symbols that we're going to use when we talk about vectors. One of the important things about a vector is how long it is. Well, if you want to talk about how long a vector is, and you do not want to draw a picture of it, you use this symbol. double bars. When you put double bars around a vector, it means the magnitude or the length. So that is the symbol that you use to describe the length without actually drawing it out.
So like absolute value?
Well, it's like a double absolute value. Yeah. So it's a little different. It's got like an extra bar in there. The other thing that's important is because you're talking about length, you can never have a negative number for the length. Doesn't make sense. When you measure something, it's always positive. So, what would be the difference between these two answers? If you wrote down this answer on a test and then compared it to this answer.
They're just opposite directions.
So what would be the difference, though, between the two answers?
One's flipped.
What you said might, well, yeah, what you said, it does not describe the answers to this problem. Remember, I am not asking about the vectors. I'm asking about the magnitude of the vectors.
Oh, the magnitude would always be negative.
They're both the same.
Well, magnitude's always positive. They're what?
They're the same.
They're exactly the same. So these two answers are equal to each other. Are the directions of the original vectors different? Yes, of course, but that's not what the question was asking. It was asking how long is each vector. Yep. All right, so that's one symbol that we use when we're not drawing vectors, if we want to describe their length. Now, if a vector has a length of 1, it has a special name. Does anybody remember what we called the circle that had a radius of 1?
Radian?
Well, it's where we talked about radians and degrees on it, but the circle had a special name. If the radius was 1. Began with a U.
Unit circle?
Unit circle, yep. So we also can use that name when we talk about a vector with a length of 1. What do you think you call a vector that's exactly 1 unit long?
Unit vector.
Exactly. It's called a unit vector. Now, earlier I told you, do not use I, J, or K when you're naming a vector. And that's because I, J, and K are special unit vectors. Okay, we're not going to talk about them today, but we will tomorrow. Okay, so vector with a length of 1 is called a unit vector. All right, and the last thing. So the last thing I'm going to show you is how you can write down a vector without drawing it. We're going to represent it purely as numbers. Well, let me show you what it looks like first. That is one way that you can represent a vector without drawing it. 2, 3. What makes that different than a coordinate? I mean, it looks kind of like a coordinate, but there's something really different about it.
The positive, negative symbols. Greater or less than.
Right, it looks kind of like like these greater than and less than symbols on each end. We call them angle brackets, but they look exactly like greater than and less than symbols. That's what you put on the ends to indicate it's a vector. Yep. So what does each number tell you? That 2 and the 3 are what we call the components of the vector. When you are dealing with 2D, which is what we're doing, we're not in 3D, there are 2 components to every vector. There's a horizontal component and there's a vertical component. If I draw a vector for you, like that. The way I can show you the components is to make it into a triangle. That dotted black line is the horizontal component. And that dotted green line is the vertical component. So if I wanted to write down that red vector in that notation, that's the vector, let's see, it's about, I'm going to say it's over here. 1, 2, 3, 4, 5, 6, 7. And then it's 1, 2, 3, 4. That red vector is the vector 7, 4. So basically what point A is telling you, or not point A, the first part, is telling you whether you go left or right from the initial point. In this case, it's a 7, which means I go 1, 2, 3, 4, 5, 6, 7. I go 7 to the right. The B is telling you up or down. In this case, B is 4, and it's positive. 1, 2, 3, 4. So you can kind of think of these two numbers as directions from the initial point to the terminal point. Tells you which way to go. And I already wrote this down up above. A is the horizontal, B is the vertical. But this notation doesn't tell you something. The notation 2, 3. It doesn't tell you where to put it. You can put it anywhere you want. So if I wanted to draw the vector 2, 3, here's one way I could do it. I could start here, stop here. That is the vector 2, 3. I could also take that vector and I could put it right there. That's also the vector 2, 3. Point is, you can put it anywhere that you want. Does not tell you where to start and where to stop. Now, out of all those different places I put it, there is one place that's most common to put it. Anyone have a guess what the most common place to start from is?
Origin?
Yeah, the origin is generally the most common place to put it. Just trying to put that right there. If you decide to start at the origin, then that is called a position vector. Any vector that starts at the origin is called a position vector. Now, what I want to do is I want to convert one of these that's not at the origin into being at the origin. And that's the last thing we're going to do. So I'm going to erase all these other ones except for one that's not at the origin. And I'm going to fix it so it is. Okay, I'm going to work with that one. Now, we already know what vector this is. It's the vector 2, 3. But we're going to pretend we don't know that. Okay. What I'm going to do is I'm going to zoom in so you can see it a little better. Should I get even? Cool. What's the coordinate of this point right there? 5, 2. And what's the coordinate of that point up there?
7, 5.
7, 5. Yep. Now, the goal is to see, is there a way that we can take those two coordinates and somehow turn them into what we already know the answer is? 2, 3. Anyone see what you can do with them?
I mean, isn't it 2, 3 right now?
Well, the vector is 2, 3, but I'm going to see how can we get that from the initial point and the terminal point. Pretend that that's all you had is those 2 coordinates, and I want you to get that somehow.
Oh, subtract terminal from initial.
Subtract, say it again?
Subtract the endpoint with the initial.
Yeah, take the terminal and minus the initial, and that will give you 2, 3.
As a coordinate?
These are coordinates. That's a coordinate and that's a coordinate. Yep.
And you,
Take the ending coordinate and subtract the starting coordinate. 7 minus 5 gives you 2. 5 minus 2 gives you 3. This is a vector. Those are coordinates.
we're trying to get the, okay.
Yeah, we're trying to get the 2, 3. Right, so this is how you do it. So if you have 2 points, call them P1 and P2. P1 is the initial, P2 is the terminal. All you have to do is subtract them. But it has to be in the order terminal minus initial. Terminal minus initial. If they do not tell you which one the initial is, you always assume it's the first point they give you, P1. And the second point they give you is the terminal. But they should make that clear in the problem. Alright, let's try an example of that. And that'll be our last one. So this time I didn't give you a picture. I'm telling you where a vector starts. I'm telling you where it stops. And I want you to convert that into a position vector. So what I would do is start with your formula, and now fill everything in. What's going to be the calculation in the first part of my vector? So 4 minus negative 1. Yep. And what about in the second part?
6 and 2.
6 minus 2. Okay. And can someone else tell me what's that going to give me for a vector when I simplify it?
5,
Yep. 5,
4.
4. There you go. So it's the vector that has a horizontal component of 5, 1, 2, 3, 4, 5, and a vertical component of 4, 1, 2, 3, 4. So if you were to draw it, it looks something like that. And that's the first part of vectors. Any question on that?
Do we have homework tonight?
I'm going to put the homework up. It's going to be whether you get it done tonight or tomorrow. It'll be
Okay.
up to you. You might end up doing 2 in one day if you don't do it tonight. But
Yeah, I see.
and you still have you've got about 25 minutes left in class today too.
Okay.
Yeah. So the homework is 1 through 10 all. The rest is evens, 14 to 22 and 26 to 32. And the directions on 26 to 32 are not going to make sense because we didn't learn something. So I put my own directions. Find the position vector. That's all I want you to do in 26 to 32.